Hi, everybody. Thanks for joining us today. Today, we're talking about building envelopes for healthy and resilient buildings in a post-COVID-19 pandemic world. Very interesting and timely topic for us today. And I will be presenting with Jay Crandall. Jay Crandall is a professional engineer and technical director of the Foam Sheathing Committee, and all-around great guy. But my role here at DuPont is in our new water and protection business, previously known as safety and construction, and work in the building envelope space with various products, insulation, air sealing, etc. So as we get started here, I'll ask Jay to move the slide along for me, and we can introduce our topic for today. We are going to talk about pandemics, how they are relevant to what we do in the building space, how they have been around for a while, they'll continue to be around and repeat themselves time and time again. We've seen as history has proven, but then also how buildings are playing a role in this pandemic world and how we see some maybe needs for improvement. So we'll talk about all of those things, and then hopefully we'll have some time at the end where you can enter questions or reach out to Jay or myself with questions after the fact. Next slide, Jay. Thank you. So all of us have been affected by COVID-19. And when we started this almost a year ago now, we thought this was going to be over in a few months. And we thought maybe the summer would kill it off and we'd be back to normal life, but that's not the way things have played out. We've been dealing with this now for almost a year, and it's affected all of us, whether or not you've been sick yourself, you've had someone you love get sick, or maybe it's affected your job, and maybe you've even been out of work for a time, or your kids are at home and you're trying to juggle both work and school. So it has been very impactful on our lives. So not just the health aspects, but many others. And I would probably be safe to say that we're all sick of it by now. So moving on and getting into a little more of the history, we have not experienced probably something of this magnitude, or this type anyway, in our lifetime. So the Spanish flu is really probably the next closest pandemic that was similar in nature to what we're experiencing today. Other things have not affected us because of, transmission has been different, etc. But now with our world becoming more global, with corporations sending people all over the world on a regular basis, and people traveling for leisure all across the globe, we're seeing transmission profiles being different. And you can see now a bunching up of the pandemic coming in the more recent time frame. And we can expect that we're probably going to see more, right? We're going to move on to the next slide. And you can see the Spanish flu, as I mentioned before, was probably the closest we had in a while. But you can read the little blurb there about the under influenza and see how similar the news story sounds to what we see today. Very ironic that back when they were talking about the Spanish flu, they were talking about the same things, about staying home, staying away, getting help as soon as possible, etc. Move on, Jay. But we know that even when we've seen this in the past, we know this is not going to be the end, very likely. We're probably going to see other occurrences of, illness in our future. Nothing is really that new. Moving on. And what we see is really kind of funny is that history has repeated itself, and in some very interesting ways, right? So very similar parallels in what we saw with the Spanish flu and what we see today. Talking about spit, who would have thought that we would see very similar verbiage and language back from 1918 and now in 2021. Onward. And masks, gosh, you know, who would have thought that we would have seen the masks? And I wasn't even familiar with how prevalent that was in the wearing of masks back during the Spanish flu. But as you can see also in the picture on your left, the woman in the light gray coat, some things never change, right? You always have a few people not quite wearing the mask the right way, even similar to today's time. But I thought some of the parallels were really funny, but serious at the same time. Next slide. Pandemics will come and go, right? But we can affect some things, and we can affect some of the future, because insanity is doing the same thing over and over again, expecting different results. But we know we can do better. We know we can do things a little differently, and this is where we can play in with the buildings and know that we can build a little differently, build a little more with improved techniques and products to ensure that we're doing everything we can to help with this problem. Next slide. And with healthy buildings, you know, there's so many different aspects of healthy buildings, and what we find is the building envelope plays a really big role, either directly or indirectly, with each one of those things. So whether it's air quality or thermal health, moisture management, etc., right? The building envelope does have an effect on these things. And so that's what we're going to talk about today, is getting into a little more how we can affect the health of our buildings, the health of our occupants, by creating a better building envelope. Next slide. And in a minute, I'm going to hand it off to Jay to get into the real meat of the presentation. But as you do start thinking through Jay's slides, think of the building envelope as the protective skin on the building, and that the HVAC system is more like the lymphatic system or the respiratory system, where the skin is providing that exterior protection. Jay, next slide, and on to you.
Okay, thanks, Amy. That was great. Just to see those parallels, and you know, I think we're in a situation where we are able to make some advancements in the way we deal with health in buildings because of the knowledge that we've gained since 1918. But to the point that there's a lot of indirect and direct relationships between the building envelope or even the HVAC systems. You know, one of the things that building science is supposed to do is to integrate all of the scientific knowledge that's relevant to a particular building technology topic and put it to action, put it into use. And from the whole building design guide, this chart, pyramid, sort of shows a sequence of priorities in design, where the health and safety priorities are at the bottom, and then more the aesthetic type things at the top. But what that fails to do is look at the interactions. So health and safety is more than just keeping a building from collapsing or dealing with fire. For example, if you look at the top of the pyramid, the well-being aspect is what we're going to be talking about a lot today. That's where health comes into play. And when you look at the ability to use the building environment to control the risk of disease transmission, then you start to talk about things that relate to health and safety, because disease transmission, as we've learned so unfortunately in the past year, can result in death. And we'll talk a little bit more about the role that buildings have played in that. And that gives us some insight in what we can do with that building environment to deal with the health and safety issues of being in a building. Just to mention real quick, you know, hygrothermal performance, you know, dealing with moisture control in your assemblies and durability, that's also a health and safety issue. Ultimately, if you build a strong building, but it rots or has moisture issues and falls down in 50 years, that's not so good. That's a safety issue. So all of these have important interrelationships. And so before we dive into some of the specific building science type applications to the building envelopes and HVAC systems, I thought it would be good to go through a review of just 3 areas of science that sort of build the case for taking some action to improve the healthiness of buildings. And we'll start with sociology, which is the study of human behavior. Then spend some time in the area of biology, which just covers a lot of ground, including virology, but generally the study of life and living organisms. And then economics, that's a science as well, and we always have to balance what we're doing with the economics of being able to do it. So first, in the area of sociology, I think this is just the point here is that we spend a lot of our time in buildings based on national surveys of what people do. 87% of the time we're inside of a building of one type or another, whether it's an office, restaurant, and particularly our homes. And you can see that homes, our time inside our house occupies about 2/3 of our time. So I don't think it takes a whole lot to conclude that indoor environment is actually pretty important to our health. And I think it's also important to this issue of disease transmission. Looking at a database of about 2,000 documented super spreader events. This is where you have multiple people infected by, one or just a few individuals. And I think it's interesting that in that database, it's a worldwide database, nearly all of those events were due to indoor and transmission of disease in an indoor environment. Particularly, most of those were where you were in a confined space for an extended period of time, whether that's something like a bus or a crowded restaurant, or and also that they occurred at a higher frequency during the flu season, which is fairly typical for viruses. They have different seasons where they're able to survive or transmit better when they're outside of their host. So sociology says we should be concerned about our indoor environment. Biology, so just the basics here. We all need oxygen, we all need water, we all need food. Pretty much every living organism needs those things to survive, but protection is where we start to talk about what we can do in managing risks. So we need protection from extreme temperature, from solar or UV radiation exposure, hazards of various types, but in particular what we're going to focus on here is our pathogens, things like bacteria, viruses, molds, those types of things that will exist within the building environment. And here, I think one thing that's happened over the past years, people have gotten very familiar with what the SARS COVID-2 or coronavirus 2 looks like. And so we have that here on an image of it, but also other pathogens that can cause disease or health problems in buildings include bacteria and mold. So molds and bacteria, they're prolific. They just exist about everywhere in almost any type of environment. But they particularly will survive inside of buildings when the conditions are conducive, and that relates to what's the temperature, humidity, and is there a food source for them. So molds and bacteria tend to have an optimal temperature and moisture condition for them to survive. And so that's important to know when you want to establish some targets for designing your indoor environment. Viruses, on the other hand, they do require a host to replicate and propagate. They've got to be inside of a living organism. In fact, believe it or not, viruses can infect bacteria and reproduce themselves. It doesn't need to be like an animal or a human. But this just gives an example of how viruses replicate. It's an electron microscope image. This is the surface of one kidney cell. And there are billions of cells in your body, right? This is the surface of one kidney cell producing the blue dots are the coronavirus. And you can see how effective that virus, and many like it are able to reproduce itself and spread the infection throughout the host. And then, of course, the next step after the host is infected is infecting others. And so viruses become a part of the building biome, or the ecology of a building, so to speak, by us, an infected individual, shedding body fluids. And that, the common example is coughing. You can project body fluids quite a distance by coughing. And if the conditions are right, it can go several tens of feet, being carried in airflows, the smaller particles, while the bigger particles drop fairly quickly. They're still going to be in the building as a droplet on something. The amount of activity you have, whether you're exercising or singing versus at rest, is going to determine how much shedding is going on and how much of a burden of a potential pathogen might be building up inside of the building, separate of any other treatment or removal going on. Even flushing a toilet, aerosolizing urine or feces can put pathogens, viruses into the air. So viruses exist and are transferred to others in the building environment by droplets. As I mentioned, these are the larger things that tend to hit a surface, or that if you touch your mouth and then touch the surface, it will create an infected droplet. That's called fomite transmission. And then there's infectious aerosols that are small enough or dry enough before they hit the surface that they actually float or stay suspended in the air for a considerable amount of time longer, sometimes hours. So that is what promotes an airborne transmission through the respiratory system, breathing in. Dose and exposure are important, just like seems like with anything. So if you have a short exposure to a high potential dose, your risk of transmission is lower than if you linger there for a long time, like say in a room with someone you're serving that may be sick. Your risk goes up. So dose and exposure are important. Vulnerability is important. If your respiratory system's impaired, you've been living in a dry environment, your risk of contracting the disease goes up. If you have other pre-existing health conditions, as we know with COVID, is a big factor, then your vulnerability goes up. So there's lots of factors that determine risk, some of which we can control with our building systems. And one example of that is this image here of a restaurant in one of the early spreading events in China. There was one infected individual in purple sitting at this table. This building had very low outdoor air ventilation rate, almost non-existent. So it wasn't getting flushed out with fresh air. And these indoor AC units are just recirculating units. They're not bringing fresh air in. And you can see the recirculating air pattern happening here, and how infected, aerosols coming out of from breathing and talking, maybe even shouting, laughing, whatever, this individual circulated to these rear three tables due to the way the airflow was from that particular wall AC unit. I think it was 5 individuals were infected in those back 3 tables from that one. And of course, then, the infection can spread from those 5. By the time the air had been diluted, even though there wasn't good ventilation in this other portion of the building, there were no infections of these individuals in these other parts, even though they had the same airflow going on from their AC units. It did not spread that way. And this is the dose exposure issue. And I think even the servers for the table, because they were not lingering in this vicinity for a long time, did not contract the disease. So just an example of some of the things that we're learning from the event. And that's not the only one. There are many like that. So the other thing that's important I mentioned earlier is that, bacteria, viruses, and molds have certain environments where they tend to thrive, and others where they don't do so well. Fortunately, that range where they don't do well, the 40 to 60% relative humidity range, is the range where we do best. And our respiratory systems are are not impaired as much by being too dry. So this range here in this chart, the gray range, is kind of where you'd want to target the control of your indoor environment as far as relative humidity is concerned. We'll talk about other things there, but the reason for that is that it de-emphasizes survival of viruses and bacteria and molds, and emphasizes the healthiness of our respiratory systems. So this chart shows 30 to 60%. I think that comes from the building envelope interest side of this, because they know if we have higher humidities in the winter, it can create problems in building envelopes if you don't design them to deal with that. But in terms of focusing mainly on human health, the range we should be shooting for is 40 to 60%. The other thing that's interesting in the area of biology is that, like us, bacteria and molds and viruses don't do well with an overdose of UV light, particularly in the range of about 260 nanometers. And so UV light is an effective germicidal treatment for indoor air or surfaces even. The problem is you don't want to treat the humans at the same time. But this has been, and there are ways of doing that. We'll talk about that later. But this has been known since the 1800s. There were experiments done back then at the ability to work as a germicide. Discovered it actually worked pretty well. And in fact, in the 1930s, you can see this image down here of this schoolroom that was equipped with what they call upper room air UV treatment. So you're not casting the UV light on the students in the room, the children in the room, but on the air up above. And so you get this treatment effect as the air circulates in the room. And interesting enough, they found that during a measles outbreak that happened during the course of their experiments, and measles, by the way, is a considerable amount more transmissible than COVID-19 by airborne transmission. The transmission rate of measles in rooms without the UV treatment was 50% of the students got it, whereas in the rooms with the UV treatment, only 15%. So you can see it had a significant impact. And I think that this is also important to realize that when we wear masks, it has an impact. When we social distance, that has an impact in reducing risk. When we have proper indoor conditions, like humidity, or we're even treating the air with filtration or UV light, if we go to that extent, all of those have incremental reductions in risk. And that's why we're looking at multiple actions. Social distance, mask, and even building indoor environment all work together to reduce risk. You're never going to zero it, but each action plays its role. Economics. So we'll talk a little bit about economics very shortly here, but you don't want to do something if the cost of it is too much. I mean, money also is used to deal with other health risks. So we've got to be concerned about spending too much on one issue and not having enough money for another issue. So that gets back to the definition of economics, is how society balances addressing those risks with limited resources. But I think it's clear, at least politically, we've assigned this a high level of importance. I think over $3 trillion now have been aimed at this issue just in the United States alone. That's about, I ran the math, it's about $9,000 per person, per living person in our country. Also, if you look at the data, estimates of the cost of just a common cold or flu is about $130 billion a year in health impact. Now, the pandemic, that might be something you see every 100 years, maybe 50 years, according to Amy's earlier graph. So maybe that's a $90, $100, maybe several $100 a year type of impact if you were to lay it out over the long term. And the colds and flus are costing us about $400 per person per year in terms of cost impact. That's some serious economic impact. So that means there's some serious opportunity to spend some dollars to reduce that impact. And I think that's what has been found in a number of different studies, that depending on what you do, you could easily save 25 to 150 billion a year in terms of the cost of these health impacts. And that doesn't include the energy savings when you have actions that do both, improve health and save energy. Here's another, just a quick example of a study that looked at a selection of common health issues here and their impacts and coordinated with energy efficiency improvements reduced the impact of certain health issues and had a positive outcome over here on the right. And just running the sort of economic analysis of those effects through a representative sample of, say, 200,000 homes that would benefit from those retrofits, the economic health benefits would be about $600 million over the course of 10 years, certainly justifying doing things even for retrofit, not just for new buildings. And the dollar return on the investment is about $3 for every $1 invested, based on the estimates that we have available. So the economics do justify taking action. I think, you know, part of the challenge here is it's difficult to precisely quantify the benefits, but we know they're big, and I think, you know, that should justify taking action, even if we can't agree with a great degree of precision on what those impacts are when from an economic standpoint. But even though those impacts are big, we need to be, you know, have a balanced approach where we look at the, you know, the cost effectiveness of implementing any measures that we think would improve health and reduce the risk of disease transmission in buildings. So we're going to talk a little bit about building science applications and the role of heating, ventilating, and air conditioning systems in buildings. So, you know, the objective with your HVAC system design is to control the indoor air quality. And air quality is measured, you know, in traditional ways, temperature. You know, you want to have a comfortable temperature to live in. The set points are typically 68 degrees Fahrenheit for heating, although some people like to crank it up, and cooling 75, although some people like to crank it down from there. Those are our targets we shoot for generally. Mechanical ventilation, the code has minimum requirements for how much outdoor air needs to be circulated into the building, along with your indoor air recirculation while you're, you know, conditioning the air. And then your indoor air hygiene is important. That's why we have filters in our systems. And that sort of dictates what the particulate burden is in your indoor air, you know, how well it's filtered. It also keeps your equipment clean and working properly. And then your indoor air humidity levels are also important for reasons that we talked about earlier. But even getting all of these things perfectly right, they don't zero your risk from a health standpoint. So during pandemic, I just want to give the caution here, we still need to be practicing, you know, good intervention to help reduce the risk, such as, you know, mask wearing and social distancing, even inside a building that's well designed to control those risks. So one of the ways to control the risk with your HVAC system is your outdoor air ventilation and the portion of outdoor air that you bring into the building as it's being conditioned. And that can be done by mechanical ventilation or by natural ventilation or a combination of both. The more ventilation you bring in, the more you dilute that air, but also then the more heating or cooling penalty you're going to pay to recondition that air. So there's a balance. There's an economic balance here, a trade-off in how much outdoor air you bring in. Many of the recommendations that you'll see from ASHRAE and others would be that, you know, the minimum outdoor air ventilation required in the code is generally adequate if you combine that with good filtration, a good filter. But, you know, in conditions where you might have high occupancy during a party or an event, it's probably a good idea to increase that ventilation rate. And there are different strategies for doing that: opening windows, leaving your fan running, if you have outdoor air, leaving it running so that outdoor air is constantly circulating in. And of course, that may depend on the weather, whether you can do that or not. Filtration is important. So the filter on an HVAC system is like the mask on your face. The mask is always working because we're always breathing. If we're alive, we're breathing, and we're filtering the air through that mask. On the other hand, the HVAC system is only filtering the air when the fan is running. So if you're in a mild temperature condition where your set point's not calling your equipment to run, then it's not filtering your indoor air, and you're not getting the benefit of that mask that you get from the HVAC filter. So one of the options would be in those conditions to run your fan so that you're getting that filtration effect, and that'll help clean the air. But you've got to have the right filter to do that, and we'll talk about that in a minute. The other thing you want to do is avoid high velocity flows, like a directed flow to an individual that would cause airborne transmission to happen more effectively, maybe over 10 feet instead of 6 feet. So getting good air circulation without, airflows, high velocity airflows is important. And that has a lot to do with how your grills are shaped and where they're directing the airflows. So filtration efficiency. Typically, homes, I'll say, are probably your run-of-the-mill filters down here around what's called a MERV 5. That's an ASHRAE particulate removal efficiency rating. And so you're only, as far as viral size particles, you're only getting maybe 32% filtration efficiency in the way they measure it. Not very good. So, typically you're going to see folks say, hey, you need to use a MERV 13 or better, or HEPA filter. And a MERV 13 is equivalent to about, I think the Home Depot rating is called an FPR or something. It's around a 10 FPR is often recommended as, sort of the thing you need to use in your house. The problem is, and we'll talk about that in a minute, is when you get better filtration, you tend to pay a penalty with, now you've got more resistance to airflow, and there's some impacts related to that. So MERV 11, something about in this range, is certainly better than the MERV 5, a typical filter, and still gets 78% filtration efficiency for viral filtration. That's what I'm using on my house. I tried the 13 and it didn't work. My system couldn't tolerate it, and I'll explain why later, because of the pressure drop that it created. But we were able to find a MERV 11 that would work, and so that's what we ended up using in our particular house. But MERV 8 also still would be somewhere around here on the curve, is also still pretty good. If you can't tolerate a MERV 11, a MERV 8 is certainly better than a MERV 5. That would still get you above 60% filtration efficiency. And if you have decent outdoor air coming in, and you social distance and wear a mask, if you're having a group over, then that may still be, that's still going to reduce your risk better than doing nothing. So the filtration pressure drop, as I mentioned earlier, can be a problem with trying to retrofit a system that wasn't designed for high efficiency filtration, because you get this pressure drop. It can cause your ductwork to can. It'll cause your fan to work harder and lose the flow that you designed for to get your conditioned air and ventilation air flow rates into your rooms. So it could, if you just go plug in a high efficiency filter and you have a lot of pressure drop, it can really harm the operation of your HVAC system. And the point here is you're going to have to work to find out what your system can tolerate, unless you're designing a new building where you can design the system to handle the higher filtration efficiencies, and use a bigger filter, and you've got less resistance to the airflow through it. One thing I've learned is not all filters are equal. So you can have a MERV 13 filter that has a pressure drop, high resistance up here, but also a different brand has a pressure drop that's down here for the same MERV 13 filter efficiency. You know, more than a factor of 2 difference in your pressure resistance. So that's not incorporated in the ratings. So you might have to get the manufacturer data to figure that out. But there are filters that can give you high efficiency with low pressure drop. So you might, you know, just to be aware of that. What if you don't have a forced air heating or cooling system? Then you've got to use portable air cleaning. And there's a lot of options out there. Again, some are better than others. Consumer Reports would give you information as to the filtration efficiency of the different types of units. They're also good for quarantine rooms. If you've got a sick person in your home you're taking care of, it'll reduce your risk if you have one of these systems in the room. I mean, of course, if you've got good ventilation and you've got the room set up to be under negative pressure like a hospital quarantine room, then also all the better. UV treatment, again, this is something that it definitely works, will help reduce the risk, but generally the costs and the energy penalties of running UV light systems sort of relegates these to applications where you have high risk, you're crowding, you know, people are frequently crowding to help treat, like a schoolroom, for example. You can put these in duct systems where the air flows by this UV treatment portion of the duct, and they have to be designed to get the right dose, the length of lights, and be installed in duct. They can be put in upper air rooms. There are portable treatments that can be done with a portable unit, kind of like the portable air filters. But you know, these systems kind of need to be designed to get the effect that you want to have in terms of how effective it is in debilitating the airborne virus. Indoor relative humidity. Of course, you know, in a new building, you can design units into the HVAC system for humidification or even dehumidification to help control this health, try to hit this health target of 40 to 60%. You know, most homes now, they don't have any control on humidity. You just have a temperature set point and the humidity is what you get. And even with humidity control, for example, there's a picture of a dehumidifier in my crawl space, and obviously in the wintertime it doesn't run. The humidity down there is about 35%. That's fairly low. You can see during a cold, dry period, it got down to 34% in the upstairs area, but I'm generally trying to maintain it near 40%. It's difficult to do that. I would need to add a little bit of humidification to the home to do that, but it could be done. My point here is that you're not going to have perfect control. There's trade-offs in the amount of ventilation you're getting, how fast the wind's blowing, how well your building envelope, how tight that is, so that you don't have these outdoor factors affecting your ability to control indoor humidity. So your envelope tightness is important. Occupancy conditions, how many people, how often do they take showers, and then your outdoor air, ventilation rate. And are you running your exhaust fans, or do you have an automatic ERV system, for example, exchanging outdoor air? So, you know, here I'm showing sort of more of a manual control approach where there's portable devices and the ability to sort of monitor conditions. It can be automated with equipment, having a thermostat and the equipment with humidification control all built into your humidistat and thermostat. But regardless of what system you're using, maintenance is important because these are things that are dealing with water. They're introducing water. They're trying to remove it. You've got condensate that has to be removed, and those are all areas where molds and things can build up. So those become systems that need to be maintained. So you solve one problem, potentially create another without good maintenance. Indoor air quality, basically this is a quote from the Indoor Air Quality Guide from ASHRAE, and it kind of speaks to some of the points I was making earlier, that, you know, the best time to address these are when you're designing the new building and building the new building. After that, it becomes difficult. It becomes hard to get the right filter because of limitations in your HVAC system. The example I have here is it's difficult to run at 40% humidity. Say if you're up in Chicago and the building envelope wasn't designed to handle the vapor pressure differential that you get when you're trying to hit 40%. relative humidity, you could start to have moisture problems in your building envelope. And but they're easily resolved with proper design and new construction. But the building code, the heating, ventilation, air conditioning, the energy code doesn't require you to have these health set points met for humidity. So let's talk now about how the building science application sort of ties HVAC system design into building envelope design. So the primary role of the building envelope is to separate the indoor from the outdoor environment. And without a good building envelope, all of these things I talked about earlier, like trying to control humidity, trying to control your ventilation rates and filter the air and have good air quality, all of that becomes more and more difficult and even costly from an energy penalty if you don't have a good building envelope to support the systems that control the indoor environment. So the benefits of a good building envelope are you get better energy efficiency. So the cost of operating a healthy building is lower. You get better moderated temperatures and humidities throughout the building. You can better control that so you don't have pockets that are hot and pockets that are cold or too humid or not humid. You create a much more moderated indoor environment throughout. The better moderation of temperature and humidity within the building envelope assembly itself. You don't want to have too high humidity or moisture accumulation inside your building walls, or you could have mold and other types of pathogens develop there, or even eventually structural damage occur. So a good building envelope is going to take care of that. You're going to minimize cold and hot spots that could be small areas where mold would like to grow because it's warm enough and just humid enough, say in a bathroom, that you would tend to have that type of a problem occur. So the building envelope helps resolve many different problems with the envelope itself, but also in just being able to control the indoor environment. So over here on the right is just an example of how far you can go with it. I mean, it's a zero energy building. It's got a wall assembly like this shown here with exterior continuous insulation and cavity insulation combined together. It's got actually a double layer of exterior insulation that keeps the wall assembly warm above dew point or even high humidity conditions. That would allow you to operate this building at the healthy indoor humidity range with very low energy impacts. So all of these things can work together with the well-designed building envelope. So the building envelope, to work with a good, healthy building indoor environment, needs to have control layers to control the separation of the outdoor environment, because these two environments want to mix in the worst kind of way, and when they do, that's not good. So the building envelope control layer has to have a water control. That's like your siding and your water resistant barrier located on the exterior side of your assembly to keep bulk water out. Air control layer, so that can be your inside layer or an outside layer that's continuous, sealed to prevent air movement through or into the assembly. Best case scenario, you have air control on both sides of the assembly. Thermal control layer, in this case, the insulation is shown all on the exterior side, and then a water vapor control layer. In this case, that's also controlled by the insulation and other control layers all on the exterior side of this assembly. I picked this assembly in this case just because this is one of the most robust assemblies. This would work in all climate zones and allow you to hit that healthy zone indoor humidity without creating a problem for the envelope with this type of a building envelope system. But it's not to say that a system like this can't work. It just needs to be designed properly to handle it. So I won't get into any more detail with building envelope design and being able to properly deal with vapor flows and airflow and all of that stuff. The vapor control is fairly complex. probably one of the trickier things to get right. It's been oversimplified in a lot of sort of building science conversation and articles and things, but we do have some resources here that really get all of the parameters aligned right. Your insulation strategy, your strategy with selecting a vapor retarder related to the insulation strategy, how to maintain drying potential, how to deal with the permeance issue if you're relying on that to let vapor flow out of an assembly. All of those parameters are important, and you can get some resources here, including an online calculator that does all of that for you in a code compliance standpoint here at these two URLs that I have listed at the continuousinsulation.org website. And these are the basis of what is coming out now in the 2021 International Residential Code and International Building Code provisions. So some major advancements here to help us better integrate the building envelope with energy code requirements, and now also if we wanted to have healthier building interiors, doing that as well. So Amy, I don't know if we're going to transition at this slide or at the conclusion slide, but if you want to take it over here, you're welcome to.
Sure. Okay, that's great. Yeah, thanks, Jay, for all that great information. You definitely laid out a good case for how buildings interact from a health perspective, as well as giving us some solutions here. So this is great. Wanted to mention that continuousinsulation.org is a great resource, as Jay mentioned, for those calculators that will show you how to create a code compliant building envelope from a thermal and moisture perspective. So that's really, really super helpful. And also the report which Jay created on this topic of healthy buildings, the research report, everything behind it is located on the continuousinsulation.org site as well, along with a bunch of other really, really helpful resources for your building envelope, things that promote health for humans, as well as durability and health for your building. So please make sure you check that out. And Jay, you can go on to the next slide. I'll just recap with, again, saying that it is imperative that we pay more attention to our buildings going forward, knowing that we're going to see this again, right? We're going to need to have a better environment for us to live and work in, for our kids now to go to school in, and at our homes, et cetera, and be in a better position from a health perspective. But there's all those other benefits, right, that Jay mentioned. We're also going to have more comfortable buildings. We're going to have more durable buildings, and buildings that aren't going to create some other issues from a structural perspective, et cetera. So all of those things do matter, and we thank you for listening to the presentation. We hope that you found it interesting, and we hope that you actually have some feedback and some questions for us. So I'll let Jay go on to the next slide. And please do submit those comments, those questions to Jay and I, or through the RESNET system, in order to let us know what you think and help us help you a little bit more on this topic. And with that, I think we will sign off, and thank you very much.
Yeah, thank you. Thanks, Amy.